I'm Raj Modi and we are going to talk about Ipyvolume. It is a Python library built on Ipy and WebGL. So the main use of Ipyvolume is to visualize 3D data and make amazing graphs and different type of plots like scatter plots, mesh plots, and quiver plots. So this is used in different fields like scientific computing, data science, and any other field which requires an in-depth volume analysis. So one of the main features of Ipyvolume is how interactive it is. We can easily zoom in, zoom out, animate different stuff using Ipyvolume. So now let's talk about some key features of Ipyvolume. First of all, its integration with Ipy. As Ipyvolume is built on top of Ipy, we can easily integrate both of them as seen in this example. So we have used a widgets.float slider to create the size slide bar, from which we can change the size of the scatter plot. Now let's talk about the second key feature of Ipyvolume. It is animating series data using Ipyvolume. As you can see in this example, we can animate this scatter plot in how we want. We have just used ipy.animation control and used our quiver plot in it. One of the most important features of Ipyvolume is its integration with bqplot and wax. When in real life, when we have large data sets, we use bqplot and wax to visualize that in 2D. Then we use Ipyvolume to better visualize it in 3D. Over here, we have taken around 2.5 million New York City taxis data and plotted this heat map. Moving on to the fourth most important feature of Ipyvolume is its So coming on to the fourth key feature of Ipyvolume is its use to plot different trajectories and curves which cannot be easily visualized using 2D structures. So we have taken an example of a helix over here, so which is rather difficult to see it in a 2D plane. So it is basically a sine and cosine wave moving with time. And this can be easily plotted using only 2 or 3 lines of Python code. But it is only possible because of Ipyvolume.
Let's take a hands-on example. I'm going to simulate our solar system using Ipyvolume. Here, I have used libraries such as Ipyvolume, NumPy, and Ipy. Now, I have defined some real data, those steps. These are planets. These are color RGB values. I have put RGB values for each and every planet to get some real colors. These are actual densities of our planets in gram per centimeter cube. These are semi-major axis, eccentricities, inclinations, real diameter, real radius, and orbital periods in days. The radius are in kilometers. Now I have to define scale factor for both distance and size to get better visualization. So the scale distances are this, and major axes are this, and scale radius is this. Now I have to define angular speeds and time to get the animation. So the angular speed is basically 2 pi divided by orbital period. I am scaling up by 50 times to get the better visualization, because in the real world, if you see, you will see very slow moving planets. So I am scaling up with 50. I have defined a time array which is np.linspace 0 to 1000 pi, and I am dividing it into 6000 frames. Now, to store x, y, and z positions of planets over time, I am initializing 3 lists. Then I'm iterating over each and every planet. I'm getting theta as omega into t. This is the formula for theta, and this is the r, which is the elliptical orbital radius of each and every planet, which can be calculated by Kepler's formula. So this is the formula for r. Now we have to define x orbit, y orbit, and z orbit. So now we are taking xy plane as the reference plane. So the z orbit is initially 0. X orbit is r cos theta, and y orbit is r sin theta. We have to tilt y orbit and z orbit to get the inclination. So by this we can visualize this entire structure into 3D. So this is the mathematical formula for tilting the y-axis and tilting the z-axis over here. Now I am appending those data into x, y, and z. I have to take the transpose of x, y, and z, because in the first step, when we do x dot append x orbits, it's the numpy planets, comma, numpy time steps array. Now for animation, we have to take the transpose to make numpy time steps, comma, numpy planets. I'm using Ipyvolume over here. I'm defining a figure as ipv.figure. This is the figure object, and this is the planet scatter object, which will give the scatter plot of each and every planet. So this is the syntax ipv.scatter xyz. I'm defining the size as scaled ready. So each and every planet will get the size of the scale radius which we have already defined over here. So like Mercury will get its scale radius and Jupiter will get its scale radius. So Jupiter will look bigger than Mercury. I have defined colors as colors RGB, which I have already discussed. Now, to plot the orbits, to plot the inclined elliptical orbits, I am again iterating over each and every planet. Now, this is the theta full, which is equal to 0 to 2 pi to make a full rotation, and I am dividing this into 100 parts to get smooth ellipse. Now, here is again R full. R full is basically the same as previous R, which is calculated by Kepler's formula. X orbit, Y orbit, Z orbit are the same. Y tilted and Z tilted are the same. Now I am plotting X orbit, Y tilted and Z tilted. I'm giving the color as gray. So it will plot here. I am creating a drop down menu to select any of the planets and get some information of the planet. This is the function which I made to get some information of the planet. I am creating a slider frame by IPY widgets to interact with it. So I am adding the information in the drop down. So whenever the user chooses any of the value from the drop down, it will show its information like the selected planet, coordinates, size, density, and orbital period of that. And I have created a slider to get coordinates in real time. Like if I increase the time frame, then it will change the coordinate in real time. Animation control planet scatter comma interval equal to 100 to animate this thing. Planet scatter was the object which contains the scatter plot, and I am defining the interval equal to 100. It is the interval between the two frames. I am using the style as dark to get better visualization because the outer sky is dark, and this is the IP.show to show the entire thing. So this is the output which we are getting. We can rotate it, we can zoom it and see that the sizes are relative and as per the real data. Like this is Mercury, this blue one is the Earth, and this is the Jupiter. Now, if we play this, now you can see these planets are moving as per the real speed and in the elliptical orbits. You can see over here all the orbits are elliptical and inclined at a particular real angle.
Hello, I'm Soumil Shah and I have worked upon this exposition assignment. So, in conclusion, I would like to say that in today's rapidly evolving data science landscape, the ability to visualize and interact with complex data is more important than ever. That's where Ipyvolume comes in. The powerful library allows users to create interactive 3D visualizations that make it easier to explore and understand intricate data sets. From simple scatter plots to dynamic animations, Ipyvolume transforms raw data into compelling visual stories. Now, in our project, we modeled a real-life solar system using Ipyvolume, which demonstrates capabilities in visualizing real-world complex systems. By utilizing real orbital data, we created a scaled-down and miniaturized version of the interactive solar system, bringing celestial mechanics to life in a way that static plots simply can't mimic. Uh, Beyond astronomy, hypervolume also proves invaluable in various fields. For example, aerodynamics and industrial design. Its quiver plots, for example, visualize vector fields in a way which are crucial for understanding airflow dynamics and optimizing designs. Now, talking about references, we mainly refer to four references. First one is the official Ipyvolume documentation. The second one is a blog article which we use to take inspiration for data visualization. And the third and fourth ones are mainly used to gather the real world solar system data for our project assignment.